In this lesson, we're going to talk about projectile motion. Now, projectile motion is dealing with, as obvious as it sounds, projectiles. Now, projectile is defined as an object that is thrown or projected into the air, and once it's in the air, the only force that's acting on it is the force of gravity. We could include air resistance in that, but the calculations rapidly become far too complicated, and so for the scope of National 5 physics, we're going to ignore air resistance altogether, and we're only going to be dealing with the effects that gravity have on these objects. So how would you define an object as being a projectile? Well, something, for example, like if you go to the top of a very tall cliff and you could throw a small ball bearing or a tennis ball, anything like that. So throw the tennis ball off of the top of a cliff, and it's going to follow a path, and a very, very specific path. So we've got our cliff up here, and if we throw the ball, it's going to curve down until it hits the ground below you. Another example, well, you could be standing with a football, and you kick a football, the football is going to curve up, and then as it's moving through the air, it's going to curve up, follow a curved path, and come down again. Now, the defining thing about this is that in both cases, with the tennis ball moving from here down to here and a football coming from up here down to here, is that as soon as you have imparted that force, now that force is going to be applied for a very short time with your hand or your foot, but as soon as it leaves contact with your hand or your foot, then you're not applying a force to it anymore. And indeed, the only force that's going to be acting on that is going to be the force of gravity. For the purposes of National 5 physics, all we are going to be looking at is projectiles that are projected horizontally, or you could have a case where the object is just simply dropped. So you take an object and you drop it vertically downwards. We will not look at stuff where we're having a horizontal point and it moves up and then down. We'll come to that in higher physics when we look at projectiles again. So for the purposes of National 5 physics, we're looking at objects that are either just dropped and they fall vertically, and at that point gravity is the only thing that's acting on them. And if we're at the top of a building or a cliff or some sort of structure where there's a height and we project it horizontally, and as it moves horizontally, it's going to come and follow a curved path until it hits the ground. Now we'll look at the learning intentions for projectile motion. So we have here, I can explain that projectile motion occurs when an object has both a constant horizontal velocity and a constant vertical acceleration. So I can use appropriate relationships to solve problems, including projectile motion from a horizontal launch, including the use of motion graphs. So motion graphs, we're talking about speed time graphs. And as I've said in the introduction, that we're looking at only a horizontal launch. You will find questions where we're just dropping things vertically down. I can state that the area under a VHT graph, now VH, it's convenient to separate velocity into horizontal and vertical components, and I'll talk about that in more depth later. But where you see this VH, we're talking velocity horizontal, and so we put the little subscript H to denote that that is horizontal velocity we're talking about, because it's really important that you don't confuse horizontal velocity and vertical velocity. So the area under a VHT graph is equal to the horizontal range. That's the horizontal distance that it travels. If you project something from the top of a cliff and it moves out, falls down, then from the point that it lands to the base of the cliff, that would be the horizontal range. And I can calculate the horizontal range from an area under a VHT graph, which is saying pretty much the same thing. Now, I can state that the area under a VVT graph, so vertical velocity time graph, is equal to the vertical height, i.e. the height of the cliff. And again, I can calculate height and acceleration from VVT graphs, you should remember from when we were doing the work in motion time graphs when we started, that you could work out acceleration from a velocity time graph using the gradient of the graph. I can state and use the relationships of what we've just covered, so the area under the VHT graph, the area under the VVT graph, and then now we have two equations, which is the equation which is just speed, distance, time. If it's a constant horizontal velocity, then we can use velocity is equal to displacement over time here. And then we can also use this equation, which you may or may not remember, but it's a rearrangement of the acceleration formula. And so we have VV, so vertical velocity, is equal to initial vertical velocity plus acceleration times time. So V equals U plus AT. And it says where, and now it says where VV is a constant vertical acceleration. This is a misprint. It should say where A is a constant vertical acceleration. So we'll start this lesson off by looking at the course notes, and the course notes for projectile motion will be on page 41. There is 2 pages and pretty much everything that I'm going to talk about in the following video is going to be covered in this, and so you can refer back to that when you need to. So we would start off with saying projectile motion is defined as an object moving where the only force acting on it is gravity. And I've said before, we're going to always ignore air resistance. Okay, so as I've said previously, a projectile, if you throw a ball from the top of a cliff, we're going to have it moving in a curved path downwards. And so that certainly would be defined as a projectile. But what wouldn't be a projectile is you could have a plane flying, for example. And so a plane flying, you're having a number of other forces acting on that, such as, well, the engines would provide the thrust to make the plane move forward, but also the plane having wings, you would have a lift force created by the air moving over the wings. And so there would be a number of other different forces acting on that. It would not be classed as a projectile. Something like, as I said, a ball before, you could have a dart or an arrow. They move in generally a projectile path, although the little flights at the end of these objects will provide some other forces. They don't generally tend to provide a lift force, and so we could treat them as projectiles as well. Okay, now to start off with our projectile motion, what we need to do is, well, if we look at, let's say, an object that is projected from the top of a tall building. Now we throw this, kick this, shoot this, do something, and we start projecting it out, and it's going to move in a path that looks like this. Okay, and this is a complicated shape. This sort of parabolic shape is something that we certainly don't really want to get into start analyzing, and so it becomes much easier to then split this up into 2 different components. So as it's moving through the air, and at any point of its flight, we would have, so as the ball, say, once the ball gets to here, as the ball is here, if we were to sort of freeze frame this, then its velocity would be somewhere going down here. But we could look at this and say, well, it has a vertical component of velocity, and we'll call that VV, and it will also have a horizontal component of velocity. We'll call that VH. And so in order to do this, we must split up the motion into these horizontal and vertical components. Now, what we were talking about earlier, if we come up with a few other just of the the quantities that we're going to be looking at. So this would be the height. And I'm going to call that S. So that's vertical height. This here would be the range. And we can also say that that is a displacement. So the ball, when it gets to here, will have a horizontal displacement here. It will also have a vertical displacement of here. So it will have, well, let's start with it. At here, it will have VH. And VH is going to be horizontal velocity. It can have UV, which is going to be initial vertical velocity. VV, which would be the final vertical velocity, i.e. the velocity that it's going in the instant before it lands. It will have an acceleration. Now, for the definition of it, the acceleration of a projectile, it's being accelerated, or the force that's acting on it is gravity. So the acceleration is the acceleration due to gravity, which you should know is 9.8. And so that's going to be a constant 9.8 meters per second squared, and it's always going to be a constant 9.8. With the horizontal velocity, because this is a constant as well, then we don't need to have an initial component and a final component. It's just always going to be the same. Whatever speed velocity that it starts with will be the same velocity that it ends with. But I'll come back to that in a wee second. And finally, something that links both of these together is t, which would be time of flight. Okay, now let's look at horizontal velocity first of all. So you have an object, so you'll have a ball, and if it is, if you have it sitting on a table and you start rolling it across the table, there's no friction on the table. We're going to ignore friction altogether. So there's no air resistance, there's no friction. And so as soon as you start pushing it, it'll accelerate while your finger's in contact with it. But as soon as your finger is no longer in contact, there's going to be no forces acting on it, certainly horizontally. And if, just pretend for a second that we can turn off gravity and we can just, gravity is no more. And so the ball is going to just keep rolling along. There's no forces acting on it now. And so from Newton's first law, it says that an object will remain at rest or at constant speed unless acted upon by an unbalanced force. So this ball is moving, and it's going to be moving with a constant velocity. There's nothing to change its motion. And indeed, if we have turned off gravity, then as it's rolling across the table, it's going to be moving at a constant speed, and it's going to get to the end of the table. Because there's no gravity, there's no friction, there's no air resistance, it's not going to change what it's doing. If it's moving a meter above the ground and it comes to the edge of the table, it's just going to continue hovering in midair vertically, and it's just going to keep moving at a constant velocity until it hits the wall on the other side of the room. the velocity of the ball will not change. It will be a constant velocity. This is because there are no forces acting on it. Now, I know I'm laboring this point of saying that there's no forces, but it's really crucial that you understand what Newton's first law means and the implications of that, that if there's no forces acting on it, then it's going to remain at a constant speed. There's no air resistance, and so in a projectile, if there's no air resistance, there's nothing to slow it down, therefore the horizontal velocity is going to be constant. So let's just say horizontal. I'm going to write no force. Now if there's no force, we're going to have Newton's first law, which will mean constant velocity. Okay, now vertically. Vertically, the only force is gravity. So if we forget about the horizontal bit of the motion now, and we just think about vertical bit motion. So you take a ball, you take the ball and you drop the ball falls straight down. So as the ball is falling straight down, then it's going to act with gravity. Now gravity will always act downwards and it always acts in towards the center of the earth. So regardless of where you drop something, it's always going to come straight down. So the only force is gravity, and as gravity is acting on it, it's going to be an unbalanced force. In fact, it's going to be the only force, and so that's going to cause an acceleration. I'm going to say object accelerates downwards at 9.8 meters per second squared. Okay, so they're your basic definitions, and then as we move on now, we're going to look at how we'll actually calculate some of these numbers. So to calculate things with projectile motion, we're going to use a lot of speed time graphs or velocity time graphs. And to do that, we're going to look at the motion of the objects, and we can look at the motion both horizontally and vertically, as we've done before. So if I say here, we'll have motion time graphs, and then we can say horizontal, and then over here we'll say vertical. And if we look at the motion at a number of different points, okay, first thing, horizontal. We'll have our axes drawn like so. So we'll have time in seconds on the bottom, and we'll have VH in meters per second on the y-axis. We'll have our origin there, and now if we look at what happens if we just move this. Okay, so it's moving at a constant horizontal velocity, and therefore that horizontal velocity, that horizontal velocity, this horizontal velocity, this horizontal velocity, this one, and this one, they're all going to be the same. And so when it first starts moving, when we first project it here, it's going to have a velocity of whatever it has, VH. And then at each of these points, that horizontal velocity is going to be the same. So after the first second, second, third, fourth, fifth, sixth second, it's always going to be the same, and we're going to get a graph that is just going to have this. And so if we remember back to our learning intention, we can say they can state that the area under a VHT graph is equal to the horizontal range. So if we work out this, the area under the graph there range is equal to area is equal to area under graph, which is going to be base times height. And in our case, we're going to have, well, the base is going to be the time times VH. And if we're going to have there S is equal to time times VH. Now looking at this, and I guess this is sort of complicating things a wee bit, but if I were to rearrange this formula just for VH, I would get the formula VH is equal to S over T. And again, if we're looking here, we're going to see VH is equal to S over T. Now I don't know if you can see my mouse on this, but it's in intention 6.7, fourth line down, VH is equal to S over T, which is just our speed distance time formula. Okay, so and this is expected. It's moving at a constant velocity, and you have for throughout your entire time in physics been using speed distance time to calculate the velocity, the distance, the time of things. And so this should not be unfamiliar to you at all. So for vertical motion, let's get some more axes for a graph. Again, we'll have time on the x-axis, and we'll have VV on the y-axis. We'll have our orange down there, and looking at this. So we're going to have initially, now this is it, this is the thing, and I know we talked about this when we were looking at terminal velocity and we're jumping out of a plane. The instant that the ball is released, so the instant that you let go, when you're holding on to it, the velocity is zero because you're holding on to it. So the instant that you let go of it, it starts accelerating, but it's got to start from somewhere. And so the point that it's got to start with is 0 meters per second. And so always with projectile motion, certainly if you're projecting it horizontally or just dropping it down, then the initial velocity is always going to be 0. So time is 0, then v is going to be 0. And in fact, we could just go and we could put in there always 0. Okay. As it starts fall. It's accelerating, and it's accelerating at a rate of 9.8 meters per second squared. And so what does an acceleration of 9.8 meters per second squared mean? Well, every second the speed increases by 9.8 meters per second. So for example, if this had been falling for 1 second by the time it got to here, the vertical velocity would be 9.8 meters per second. And then after the second second, it's accelerated a bit, so it's going to be 19.6 meters per second. And after the third second, it's going to be traveling even quicker, 29.4, 39.2, 49, and so it will increase its speed by 9.8 every time. And so we're going to get a graph which looks like this. Oh, you can't see that. There we go. So you're going to get the graph which has a straight line, points up here. So it'll look like this. Going back here, so I can state that the area under a VVT graph is equal to the vertical height, and I can calculate height and acceleration from velocity time graphs. So we can use the area under a graph and this is certainly more relevant doing the area under the graph certainly than this. If you have a horizontal velocity and you have a time, it's almost easier to use the speed distance time formula to calculate the range. However, you would have to work out, you would have to draw a graph to work out the vertical height. You don't have the formulas, the equations enabling you to do that without using the graph at National 5. When we come to higher physics, we'll get a whole new set of equations which will allow us to do that, but for now we will need to do graphs. Okay, so height is equal to area under graph. Now it's a triangle, so it's going to be half base times height, and that will give us the area. Now, the formula that we have, the second formula, if we look back at our learning intentions, we're going to use this is the very, very last line in this where it says VV is equal to UV plus AT. So if we're looking at this, and I'm going to run out of space, so I'm just going to do this down here. So we have, this comes from the acceleration formula. A is equal to V minus U over T. And if we try and rearrange this in the form that is in the intentions, in the learning intentions, so we want to have V on its own. And so first of all, we cross multiply. And so that goes into AT is equal to V minus U. Then we need to get rid of this minus U, and we do that, we take it over to the other side. If we take it over to the other side of the equation, the minus becomes a positive, and we're left with, rewriting it, V is equal to U plus AT. And just so that we're super clear, if we call this VH, we're going to call this VV and UV. And so we can use this, and I'll go through a worked example just now about how we would use this, because this would be needed often to find the final vertical velocity. You would find the final vertical velocity. I'm plotting a velocity time graph here. You find the final vertical velocity, and then you know that it starts at 0, it ends up here. You can just draw the straight line down from there. Lastly, with velocity time graphs and with your vertical there, one of the intentions was that you should be able to calculate acceleration from the vertical time graph. And so to do that, we would have acceleration is going to equal the gradient of the line. And the gradient of the line would be y2 minus y1 over x2 minus x1. Okay. In the next section, we're going to be moving on and we're going to be looking at some worked examples of projectile motion. So in this, we're going to look at some worked examples of projectile motion, and we'll start off with a really straightforward example where we have a building, and we can see that our building is 100 meters tall. We take an object and we drop the object off of that building. So example 1, calculate the final vertical velocity. And so we would use our formula V is equal to U plus AT. Now remembering back to the earlier part of the lesson, there is no horizontal velocity, we've just dropped it straight down. And so the initial vertical velocity is always going to be 0. And the acceleration is always going to be 9.8. And then we're going to calculate the final vertical velocity. So we have our formula here. U always going to be 0 plus, and even though it's always going to be 0, we must include it in the equation. The SQA will penalise you for not including that. The formula is not V equals AT, so you must include the U and you must include the 0 in the first line of the substitution. And we have 9.8 times, oh sorry, I should have said, we need to know that it is falling for a time of 4.52 seconds. Okay, that's better. 4.52. That will give us 44.3 meters per second. Now, if you remember back when we were looking at conservation of energy, and we did an example, and this is where we climbed up with my backpack and we dropped the ball off of there and we worked out the potential energy, and eventually we got to the energy, the final velocity of the ball just before it hit the ground, 44.3. It's falling off of a 100-meter cliff. In this case, we had mass, and we used the mass throughout. And then a little bit later on in that lesson, I did another example where we cancelled mass out. Now, if we're ignoring air resistance, which we always do, if we're ignoring air resistance, then the mass of an object is irrelevant. We could drop a piano off, or indeed we could drop a feather off, and they would both accelerate and they would both hit the ground at exactly the same time. At the end of this video, I'll give you a couple of links to watch. There was an experiment that was done. It was one of the things that when in the first moon landing they took a hammer and a feather up, and they wanted to do this test because on the moon there's no air resistance, and so they took the feather and the hammer and they dropped them, and they both fell at exactly the same rate to prove that the physics was right. And so there'll be a video there, and then there's a Brian Cox video who does exactly the same thing, although not on the moon. He goes into a large vacuum chamber. So there's two videos there, which I'll put a link to at the end of the video. But needless to say, this method works for calculating the velocity after falling from a height, as does this method. You need to pay particular attention in a question. The question may say using conservation of energy. So if it says calculate the final velocity after falling for however long, it says using conservation of energy. So if it says using conservation of energy, you must do the energy way rather than the projectile way. Okay, so moving on, example 2, we'll do another one. And we can say calculate height of the cliff. And so here we have our cliff. There we go. And we take our ball and we're just going to drop it again. We're just going to keep things really, really simple. And we're going to say that it's falling for a time of 3 seconds. So in order to calculate the height, we need to know, first of all, final velocity. So we need to know the final velocity, and we find the final velocity with, V is equal to u plus at. U always 0, must include it. A always 9.8 times, our time is 3 seconds here. And so that's going to be 29.4 meters per second. So it starts at 0, it finishes at 29.4. What we now need to do is, number 2, draw VT graph. Now you don't need to do a fancy graph, a very, very quick sketch. Just scribble it out. Make sure you do though put labels on your axis, v ms to the minus 1. So we'll have our y unit, our x unit, our origin, and then we can start. We know it starts at 0 up here. We know it finishes at 29.4. That's up here. We can draw our line. And then we just need to work out the area under this graph. So we can say height is equal to area under graph. And that's going to be a half base times height, which is then going to be a half. Now our base is falling for a time of 3 seconds. It gets 29.4. So base 3 times 29.4, which is going to give me 44.1 meters. Now I'm going to add in here, just because I can, plus calculate acceleration. Well, I've already used acceleration there, so I already know what it was, but because this is a worked example, I can do what I like. And so I'm just going to show you the calculation and how you would do that to work out acceleration. So calculate A, we'll have A is equal to gradient, which is equal to y2 minus y1 over x2 minus x1. Sub in the numbers here, so our y2, well, if this is y2x, x2 y2, then the y coordinate is going to be 29.4 minus, and our y1 is going to be 0 over our x2 is going to be 3 minus 0, and that's going to give us, when we work it out, 29.4 divided by 3 is going to give me 9.8. And we're not going to forget the unit of acceleration, which is meters per second squared. Okay, so we now have everything that we need to calculate the vertical motions of objects falling with projectile motion. And so we're going to finally look at one worked example where we have an object that's projected horizontally. So again, let's come up with our cliff. And so we're going to take our object. I'm saying our object. It's going to take our ball, because we always use a ball, and we project it horizontally. Let's just kick it this time. So we're kicking our ball at 12 meters per second. So our initial horizontal velocity is 12 meters per second. Now it is so crucial that you never mix up horizontal velocity and vertical velocity. Remember, initial vertical velocity is always 0. You don't get to use 12 or any other number for vertical velocity. At the moment, this is the horizontal velocity, and you can only use it horizontally. So in fact, what I'm going to do, I'm just going to split my page up here, and I'm going to call horizontal, and I'm going to put vertical over here. Oh, we need to know what we're doing. So we're going to have example 3. And we're going to say calculate the horizontal calculate the horizontal range and the height of the cliff. Cool. And we need to know that it is going to fall, or it's going to be in flight for a time of 6 seconds. So horizontally, it's going to be traveling at 12 meters per second for 6 seconds. And so as per their learning intentions, it wants us to draw a velocity time graph. Again, quick sketch. That's all we need. 0 VH ms to the minus 1 time seconds. It's going 6 seconds here and it's going at 12 there. It's constant, and so we will just have a graph that looks like this. And then we're going to say range is equal to area on the graph, which we're going to have base times height, which we're then going to have 6 times 12, and then that's going to give us, oh goodness me, is 72. That's shocking. My 12 times table, I'll need to go and learn that again. 72 meters. Now you would be absolutely bonkers to try that and do that when you know full well that the horizontal range S is going to be VH times T, which is going to give you 12 times 6, which is going to be 72 meters. I don't think I would ever try and do this drawing out a velocity time graph, and too much. Just keep it really, really simple as you can. And the simplest method of working out horizontal range, if you have the horizontal velocity and a time, is you just use speed distance time and move on. You're done. Now, vertically speaking, so what do we have vertically? We've got to find out the height of this cliff. What's its initial velocity, vertically speaking? Right now, if it was in class, half of you would be saying, yeah, it's 12, it's 12. But no, our initial velocity, vertically speaking, is always 0. Final velocity, well, that's what we're going to want to find out. Our acceleration is always 9.8. And our time, 6 seconds. So we have everything we need. V is equal to U plus AT. We're going to have 0 plus 9.8 times 6. And that is going to give us 58.8 meters per second. Then we come to drawing our velocity time graph. Quick sketch. No. So we know 6 seconds. Final velocity we've just calculated is 58.8. And we're going to say height is equal to area under graph. And that's going to be a half base times height. It's going to be a half times 6 times 58.8, and that's going to give us a total of 176.4 meters, and that's us done. Okay, so that's the projectile lesson, and what we'll do is I'll set you off to do some extra work, and then there'll be another video which will cover the worked examples in the course notes. Just before I go, now I mentioned that there's the 2 videos about why mass is unimportant of objects following gravitational fields. But there's a third video which I would like you to watch. It's called The Monkey and the Hunter. And what the basic premises of that video is it's something that you wouldn't necessarily think of. If I just get this back up here. So the monkey and the hunter, it kind of goes something like this, that if, so there's a monkey. It's a monkey. Okay, look, behold its wonderful monkeyness. Right, so you have your monkey and you have a hunter. Boo. And so the hunter is there. The hunter has a very large gun. Right, so hunter is standing on a platform, the monkey's in a tree. Now the monkey sees the hunter, and the monkey says, aha, I'm going to be smart, and as soon as I see him pull the trigger, I'm going to jump down. I'm just going to let go of the tree, and I'm going to fall. And the bullet's going to come out, and the bullet's going to fly right over my head, and I'm going to and so the premise of this is that you've got an object that's falling vertically and an object that's moving in a projectile path, and the physics tells us that irrespective of horizontal velocity, both objects are going to move vertically in the same fashion. And so to put this in context, you'll watch the video and you'll see an experiment that proves that this is actually the case. But the implications of this is that if you have so say you have the hunter, and the hunter is sitting there with a rifle, and they fire the rifle. Now it will be I don't know about guns, but you'll have the shell casing of the bullet, which is, if that's ejected horizontally out of the side of the gun, and then you've got the bullet which travels down the muzzle, and then high-powered rifle, you'll have it traveling a mile. So it'll travel a mile and then it'll eventually hit the ground if it doesn't hit anything else. And what the physics tells us is that the bullet the shell casing that's ejected horizontally out and falls straight down, and the bullet that's traveling at 300 meters per second, 200 meters per second, will travel, and it will take the same time for the bullet to hit the ground as it will for the shell casing to hit the ground. So the shell casing lands at your feet in whatever time it takes, and the bullet will do exactly the same thing. So the bullet will hit the ground even though it's traveling horizontally at 200 meters per second at the exact same time that the shell casing does. And the video talks about that. Okay, so as ever, any questions, just ask on the classroom page or just give me an email, and I hope you've managed to survive to the end of this, and that everything was crystal clear. But as I say, any questions, just ask, and thanks for watching. Okay, bye.